Okay, students. So let's get started with what is quantum mechanics. So could you tell me, guys, what is quantum mechanics? Yes, quantum mechanics is where we are going to study the motions of microscopic objects, right? So usually all those objects, the particle nature as well as wave nature is going to be exhibited, and that makes a whole lot of difference to how we deal with motion in classical mechanics, right? So let's move further. So we look at Heisenberg's uncertainty principle. So students, can somebody tell me what is Heisenberg's uncertainty principle? Yes, guys.
Sir, there's some uncertainty to find the exact position and the exact momentum or velocity of an molecule.
All right. So suppose if we are talking about the motion of an electron, let's say any microscopic particle. Now, what is going to happen is it is not possible for us to measure the position of the particle accurately if we are able to measure the momentum. Vice versa, if we are able to measure the momentum to a reasonably good close number, we will not be able to find out the position accurately. All right, that's what the principle is all about. So it says it's impossible to determine simultaneously the exact position and the exact momentum of a fast moving particle like an electron. And there is an equation which is given, which is delta x multiplied by delta p is greater than what? H upon 4 pi. Now, what is delta x, guys?
Uncertainty position.
Yes, it's the uncertainty in the measurement of the position, or in finding out in locating the position of the electron, or finding out the position. And what is delta p?
Uncertainty in momentum.
Yeah, uncertainty in finding the momentum of the electron.
Particle.
Yes, particle, right? Now, if you see the product, right, the product is greater than or equal to a particular number, which is h divided by 4 pi, and h is a well-known number for us, Planck's constant, right? Now, if you see, what does this imply? This implies that this product cannot be lesser than this number, right? So, what does this imply is, if I am able to determine the position of the electron or any particle with a good certainty, then what will be delta x naturally? I found the position to a reasonably good extent. Then is there more uncertainty in the position or less uncertainty?
Less uncertainty, sir.
In the position, exactly. So delta x will be very low. Since the product has to be greater than a minimum number, this automatically implies uncertainty in finding the momentum becomes large. So the moment uncertainty becomes large, I cannot be certain about the momentum of the electron. Delta P, which is the uncertainty in momentum, can be written as mass into uncertainty in velocity. So I can also rewrite it as delta x into delta v is greater than or equal to h by 4 pi. I take the m to the other side. where delta x is the uncertainty in position, delta p the uncertainty in momentum, delta v the uncertainty in finding the velocity of the particle. Is this equation clear, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Excellent. So that's what is explained here. If the position of the electron is known with a high degree of accuracy, then uncertainty is very small. Uncertainty in position is very small. This directly implies that the velocity of the electron of large uncertainty, or in other words, the uncertainty in finding the velocity of the electron is quite large. Or it could also be delta p. So if the velocity of the electron is well known, then delta v is very small, which implies delta x is quite large. Yeah. Mathematically, if you see, because they are inversely proportional, delta x, if it tends to 0, then the uncertainty in momentum or the uncertainty in velocity will tend to infinity. That's what is depicted here. If delta x is 0, the denominator tends to 0, so the overall value tends to infinity. So these are all possible questions in the competitive exam as well. When one determines velocity accurately, the uncertainty in finding velocity is 0. Then when delta v is 0, any non-zero number by 0 becomes infinity. So delta x is infinity. All right. Just to explain this aspect, right? To determine the uncertainty in position or uncertainty in momentum, one should use smaller dimensions than that of electron, or it should have mass which is less than electron and should travel faster than electron. All right. So, in any measurement, if you see, right, if you want to improve the sensitivity of the measurement, for example, right, if your current is in milliampere, I'm just giving an example regarding measurement. You're using an ammeter, then obviously, the sensitivity will not be great, right? Suppose for measuring a current in milliampere, it will be better if I use a milliammeter, right? Am I making sense, guys? So if I'm going to measure some quantities related to electron regarding its position or be it momentum or velocity, then I need a particle which is not going to have mass greater than electron or almost equal to electron. It can interfere with the measuring process itself. So mass must be much lesser than that of electron. Photon is a very good particle which can be used for this measurement, right? And it should also travel faster than electron. Obviously, we understand that photons are light particles which travel with the speed of light. So that's the best. But even then, what happens, guys? When the photon is going to strike an electron and get us the measurement, right? Because how do we measure distances? I have a mirror, let's say, normally, right? What do? From, let's say, one peak to another peak, one mountain peak to another peak, I want to find the distance. What do? I keep two parabolic mirrors. Light rays falling on one, travel to the other one, get reflected, come back. I find the time for reflection, correct? That happens in our macroscopic measurements. In microscopic measurements, what's going to happen? This photon, light particles, right, are going to strike that electron and come back, right? Now, in this process, what's likely to happen is the photon is going to transfer some amount of energy to the electron. That's going to change the momentum of the electron. So whatever measurement that we do might not be accurate, is right? So I think you can understand logic behind Heisenberg's uncertainty principle, right? To a reasonable extent. So is this clear, guys?
Yes, sir.
Yeah.
Yes, sir.
Excellent.
Yes, sir.
Junior.
Okay, guys. It's clear? So it has to be an electromagnetic radiation, nothing but photons. So light with smaller wavelength than that of electron must be used for knowing the position or momentum. But when we use smaller wavelength, the frequency will be higher, the energy will be higher. Greater the energy, greater is the impact of collision of the photon with electron, right? So if the position is determined accurately, then momentum becomes inaccurate, or there is a uncertainty in its determination, right? This is something which we have got. Now we move on. So significance, if you see, because we cannot measure the position and the velocity simultaneously, we will not be able to talk about the trajectory of the particle, right? So because there is no trajectory, we will not be able to precisely say this is where the electron is going to be at a particular time t. So what is the inference? So that's why we come up with orbitals, right? This is the probability of existence of the electron, right? That's the significance, guys. Okay, then we move on to something called Schrödinger's wave equation. So this is the equation that's extremely important, which is what we call as the popular Schrödinger's wave equation, or something, a fundamental equation of quantum mechanics. All right, guys. Now this mathematical equation, you can just you need to remember the equation, of course. That's the first thing. Second thing is, as you can understand, it's a equation with derivatives, right? We have learned dy by dx. D square y by dx square will be second derivative. Okay. Now here it is not differentiation which we have learned. It is called partial differentiation. Okay. We'll be learning about that with numericals when we deal with electric fields and electric potential, which is a popular NEET question as well. All right. We will do that a little later in time. Right now you can understand. So we have a differential equation. Perfectly put, it's a partial differential equation. Okay. This is going to relate to, in a way, kinetic energy of the particle under discussion. Okay. This is a constant. E psi is going to represent, in a way, total energy of the system or total energy of the particle under consideration. And this is a measure of potential energy of the system. At this point, you can have this awareness. Okay. Secondly, this equation, when solved, right, it's a second order partial differential equation. We'll be doing partial differentiation of potential, electric potential to get electric field. We'll discuss that question later. Okay. Here we are not just forming the equation. From the formed equation, we are finding the solution. Okay. Fine. Anyways, finding the solution, we are not going to discuss at this point. Only thing you can understand is the solution of this equation is going to provide us three important parameters. What are they? N, which is principal quantum number, L, which is azimuthal or secondary or subsidiary quantum number or angular momentum, orbital angular momentum quantum number, and M, which is nothing but the magnetic quantum number. All right, guys. So these are a couple of things that we need to know. One more thing that we need to know is the symbol psi. So psi is called as the wave function. So if you are talking about an electron, each electron is going to be associated with a particular wave function. So we have learned that electron behaves both like a particle and a wave. So this will describe some parameters of the wave. Typically information regarding the amplitude of the wave. For example, if I'm going to talk about a wave, right? So this refers to the displacement of the wave, okay, at different time in time. The peaks are going to be called as amplitudes, right? This length is called amplitude. So this wave function, what we call as the wave function, is going to give us information about the amplitude of the wave associated with the particular electron, right? These are things that you need to know, guys, at this point. Is it clear, guys? Anything that you want me to explain more? Shall we move on?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
excellent. Okay, so atomic orbital wave function, psi represents the state of an electron in an atom. Whenever an electron is described by wave function, we say that the electron occupies that energy level. Okay, as I told you, the solution, right, for the Schrödinger's differential equation, which was written earlier. So psi is going to be representing the solution, and psi refers to, I told you, in the wave function format, you can say it represents the amplitude of the wave. As far as locating the electron is concerned, it helps us with three important parameters, n, l, and m. Okay, so we understand the moment Schrödinger's equation is solved for that electron, then we understand what is going to be the orbital that the electron is going to occupy. Then the parameter psi square is called as the probability wave function, which gives the maximum probability of finding an electron in a three-dimensional space around the nucleus called the orbital. Okay, guys. So I told you psi represents the wave function, or I can say the amplitude of the wave representing the electron. And psi square represents probability of finding the electron. So as you could see in classical mechanics, right, where we have all these equations, let's say I say uniform accelerated motion of a particle, then you know all the three equations, right? So exactly at a particular time where the particle will be, if it's traveling with this velocity and this acceleration, after so much time, what will be its displacement? We can find it out, right? There is no question of probability there, right? Here in quantum mechanics, you can understand because of the wave and the particle nature pronounced, we associate probability with finding the location, right? So this refers to probability wave function. So it provides maximum probability of finding an electron in a three-dimensional space around the nucleus called the orbital. And that information is provided by knowing all these three details. We are going to soon find out. Clear so far, students?
Yes, sir.
Yeah. Okay, wherever psi square is maximum, that region has the highest electron density. The probability of finding the electron is maximum in such a region. And whenever psi square is maximum, there is a 95% chance of finding the electron in that space. Wherever psi square is 0, that region, the probability of finding the electron is 0. So electron, we can be sure that the electron is not going to be there. Such a region is called nodal surface, plane, or node. Nodal plane or node. So NLM arise as a consequence in the solution of Schrodinger's wave equation. And this equation is valid for hydrogen atom or hydrogen like atom where there is one electron. So for atoms which have more electrons, this equation what we generated is not sufficient. Okay. So using quantum numbers, we'll be able to tell where the electron is located to a greater probability. As we have seen, principal quantum number is denoted by n. You can also call it as what? Energy level or shell. L represents azimuthal quantum number or orbital angular momentum quantum number and so on. It refers to subshells. And L value for a given shell will be from 0 to n minus 1. So if n is 1, then L will be only 0. If n is 2, L will be either 0 or 1. If n is 3, then L can be 0, 1, 2. If n is 4, L can be 0, 1, 2, 3. So n equal to 1 refers to first orbit. L equal to 0 refers to S subshell. Clear, guys? N equal to 1, then L can only be equal to 0. If n is equal to 2, then we are referring to second orbit. Then L can be either 0 or 1. If we are going to the third orbit, then we can have 3 subshells. 0, 1, 2. N equal to 4. Then L can be 0, 1, 2, 3. L equal to 0 refers to what subshell, guys?
Sir?
L equal to 0 is which subshell?
S subshell, sir.
Yes. What about L equal to 1?
P subshell.
L equal to 2?
D subshell.
L equal to 3?
F subshell.
Exactly. And so on. Right, guys? Then we have M. M is magnetic quantum number. So what will be M's value for a given L? M will be from minus L to plus L. Correct? So what does that mean? So here it will be for the first quantum number, right? That means first energy level. Subshell, there is only one. There's just the S subshell. So M will be nothing but minus 0 to 0 is what? 0. So that refers to 1s. So when I have all this information, I can say, what is orbital? 1s orbital. Is that clear, guys? Now, n is equal to 2. L is equal to 0, 1. What can be M? M will be from, come on, tell me, guys. When L is 0, M is 0, correct? So for second orbit, I am writing here. When L is 0, M is 0 for second orbit. Which means it refers to what shell, guys? 2s. Principal quantum number is 2. L equal to 0 refers to S subshell. And magnetic quantum number equal to 0 refers to, there is only one subshell, right? One orbital in S subshell. That's all. So 2s. Now, what are the other possible values of L? The other possible value of L is 1. What does this refer to? Come on, students, tell me. L equal to 1 refers to which subshell? Come on.
P subshells.
P subshell, very good. Now, what are the possible values of M? I told
0,
it is
1.
from what?
Is it
minus L to L. So minus 1 to 1. So it will be minus 1 or 0 or
Or
1.
one.
Correct. So which orbital are we talking about? 2p 2px. Usually I told you when you have the number 0 it is associated with z direction. So we say 2pz, and this you can write it as 2py. Correct, guys? So we know that p orbital has 3 orbitals. P subshell has 3 orbitals. So this is what is referred by this number. So if I say n is equal to 2, L is equal to 1, m is equal to 0, what is the subshell I am talking about? What is the orbital I am talking about?
Second orbital.
2pz. 2p, 0 refers to z. So 2pz. Clear, guys?
Yes, sir.
Yes, sir.
Very
Yes,
good.
sir.
Okay, guys. Super. Fine. Okay, we understand. We have already done the derivation. So Rn is equal to 0.3 n square by z angstrom, where n is principal quantum number, z is atomic number. So every orbit is going to have a particular energy, and as we move, as n increases, the energy increases. Is that clear? Clear, guys? And radius also increases. So energy of each orbit is given by minus 13.6 z square by n square. So highest negative value will be for which shell? N equal to 1. Alright, guys. When you say n equal to 2, numerically this number will decrease, isn't it? But because there is
Yes,
a
sir.
sign here, the energy is actually increasing. Clear, guys? For the first orbit, it will be minus 13.6. For the second orbit, it's minus 13.6 divided by 4. 13.6 by 4 is a lower number. But because minus sign is there, draw a negative axis. Which is greater, minus 4 or minus 2?
-2.
Exactly. So 13.6 by n square with a minus sign is greater than, you get the point, guys? For example, n equal to 2, then minus 13.6 by 2 square, 4, is greater than minus 13.6 by 1. Correct? So that's why as you go to the higher and higher levels, the energy increases. But numerical if you see, it looks like it is decreasing, right? But then because there is a minus sign, actually the value is increasing. Okay, this we have seen. Number of electrons in any orbit or shell is given by 2n square. First orbit 2 electrons, second orbit 8 electrons, third orbit 18, fourth orbit 2 into 4 square, fifth orbit 2 into 5 square, 2 into 6 square on the sixth orbit. Clear, guys? Okay. Now we come to one of the Bohr's postulate, which says angular momentum of an electron is given by nh by 2 pi. So electron cannot have continuous value for angular momentums. It only takes specific values of angular momentum. It has to be an integral multiple of h by 2 pi. And there is some reason behind that. We have already seen that electron behaves like a wave. So let's say this is nth orbit. I have told you, what is this, guys? It is one cycle starting from 0, reaching the peak, again coming to 0, going to negative maximum, and then coming back. This is one cycle. And this length is called one wavelength. All right. Now, second wavelength, third wavelength, sorry, fourth wavelength, right? So the point is exactly this must end here and again overlap with this. Clear, guys? In wave concept, this overlapping of two waves is called interference. And whenever this kind of interference is happening, okay, so this is your first wave. Let's say this is your second wave. Now you can see, let's say these two waves are overlapping. You can see at the same time, the crest of this wave is meeting the crest of this wave. The trough of this wave is meeting the trough of this wave. This kind of superposition or interference is called constructive interference. We'll be learning this in detail, right, later. However, you can understand. So for this to happen, exactly this wave must complete here and it must restart with where it started originally, right? It must exactly coincide. So if this coincidence is not happening, then electron cannot be there as a wave in that orbit. Okay, guys? So for this to happen, this is a circumference 2 pi r, and while it makes one complete circle, it must have completed n number of wavelengths. It can't be half wave. It has to be full wavelengths n number of times, where n is an integer, right? Positive integer. So 2 pi r, this entire length must be equal to n times the wavelength, all right, of the electron. So now we know that angular momentum is m into v into r. Now let's find out what is, we'll find out how to connect this, okay? So this is mv into r. From this I can write r is equal to n lambda by 2 pi. So let me write it here. This is what we call as angular momentum, represented by the symbol L. Angular momentum is known to be momentum into r. So which is mv into r, and r we got it as n lambda by 2 pi. And we know what is lambda from de Broglie's equation. What is lambda, guys? H by momentum or h by mv. So what will this lead us to? So wherever I'm having lambda, I'm going to substitute h by mv. So it will be mv n h divided by 2 pi into mv. So mv and mv will cancel. I'm going to get mvr is equal to nh by 2 pi. All right, guys. If you got this derivation, fantastic. If not, nothing to worry. You can go through this video a couple of times, okay, over. Anyways, so from this, what do we understand? We understand that electrons cannot possess any random value of angular momentum. It has to be an integral multiple of h by 2 pi. Similarly, it can't possess any value for energy. It has to be a number which is related by what we had seen, minus 13.6, right? It is divided by n square, what we had seen earlier. Z square by n square. Is that clear, guys? So it is, cannot be any other value. Okay. Other two things are quite obvious, guys. As the value of n increases, the size of the orbit increases. As the value of n increases, the energy of the orbit also increases. Any doubts till this point, students?
No, sir.
No?
No.
We'll move on. This is what I was trying to explain to you. Yeah, both ends of the wave meet each other without crossing. Okay. They do not meet, then this is not satisfied. Electron cannot exist in such an orbit. Okay. So these words you will understand much better when we do waves as a chapter, like destructive interference and all that. Okay. Right now, do not worry about it. Right now, all that you need to know is 2 pi r must be equal to n lambda. Okay, guys. Azimuthal quantum number. So as I told you, so the number of L values for a given orbit is same as n. For example, first orbit, the number of L values will be 1. Second orbit, the number of L values will be 2. Third orbit, the number of L values will be 3. Fourth orbit, the number of L values will be 4, and so on. The value of L will be from 0 to n minus 1. For example, first orbit, the value of L will be what? 0 to 1 minus 1. 1 minus 1 is 0, so it's only 0. So first orbit, L can only be 0. Second orbit, 2 values of L, 0 and 1. Third orbit, 3 values of L, 0, 1, 2. Fourth orbit, 0, 1, 2, 3. All right. Is it clear, students?
Yes, sir.
Yeah. So value of L can be only from 0 to n minus 1. This we had seen. Okay. L equal to 0 refers to s orbital, s subshell, this is s, this is p, s, p, d. Specifically speaking, this is 1s, this is 2s, 2p, this is 3s, 3p, 3d. Is that clear, guys?
Yes, sir.
Yeah. And what is this? This is referred to 4s orbital, 4s subshell, 4p subshell, 4d subshell, 4f subshell. Clear, guys?
Yes, sir.
Yes. L value denotes the subshell in the main energy level. Yes, this we had already seen. Okay, electrode filling happens based on n plus L rule. Whichever n plus L is larger, that will have higher energy. If both values are same, then the one with greater n will be higher energy level. For example, if you see 3s, what is n plus L? N is 3, L is 0, 3 plus 0 is 3. 2p, what is n? 2. P is 1. I mean L is 1, right? So 2 plus 1 is 3 here also. 3 plus 0 is also 3. Then how do you decide which is higher energy level? N, whichever has greater n will be higher energy level. That's why 3s is above 2p. Although n plus L is same for both of them. Okay. Now, the only place where you will have to carefully observe is 4s and 3d. 4s comes before 3d is filled, right? 4 plus s, I mean the sense, 4 plus 0, 4. Here 3d, what is d, guys? 2, right? 3 plus 2 is 5. So that's why this has slightly higher energy compared to 4s. So always while you fill the electrons, 4s orbital gets filled, then 3d fills. Then after that 4p. Clear, guys? Yeah, at this point, this understanding is good. This we had seen already. Okay, in a given energy level, always S energy will be lesser than that of P, lesser than that of D, lesser than that of F, lesser than that of G. For example, if I am talking about 4S, 4P, 4D, 4F, 4s energy will be less than 4p, that will be less than 4d, that will be less than 4f, and so on. So azimuthal quantum number also tells you about the shape of the orbitals. S orbital is spherical shape, p orbital dumbbell shape, d orbital double dumbbell, f orbital is a quadra dumbbell. Now obviously, when I say dumbbell shape, what does that mean? So it means the probability of finding the electron in that orbital is going to be in the shape of a dumbbell. Is that clear? That's all.
Sir, do we have any name for F orbital?
Meaning,
Like, do you have any other name like except this complex shape or something?
no, quadra dumbbell. You can have it as quadra dumbbell. All right.
Yes.
Okay. Okay, guys, it's past 9:15 now. However, I would like to extend it by another 15 minutes. Okay, guys, this also we had seen. Very simple. In a S subshell, how many electrons can be there? 2. In a P subshell, how many electrons can be there? 6. In a D subshell, how many electrons can be there? 10. In a F subshell, how many electrons can be there? 14. Is that correct, guys? So when I am talking about an S subshell, just one orbital is there, I can have 2 electrons, correct? When I'm talking about P subshell, it has 3 orbitals, px, pz and py. So each orbital can have 2 electrons, so totally 6 electrons. So S can have 2, P can have 6. When I'm talking about D subshell, it has 5 orbitals. Okay, guys, there are names to them. So if you write the magnetic quantum number, for this magnetic quantum number is 0. For this, if you see, magnetic quantum number will be -1, 0, 1. For D subshell, if you see, magnetic quantum number will be -2, -1, 0, 1, 2. And I told you, wherever 0 is there, that refers to Z square orbital or anything related to Z axis. This can be XY orbital, DXY, DYZ, DZX or DXZ, or DX square minus Y square. These are the names for the orbitals. And the reason for them, the names is because of their symmetry. Alright, guys. For example, when I say X square minus Y square, it is symmetrical about the lines X minus Y equal to 0 and X equal to Y. Right? I'm sorry, X minus Y equal to 0 and X plus Y equal to 0. So the product will be X square minus Y square. Okay, guys. Similarly, X-axis and Z-axis make an angle 45 degrees. Okay. Here it's YZ. So there is a reason for the sign convention, I mean the naming. So each orbital can have 2 electrons, guys, making 10 electrons. For F subshell, 7 orbitals are there. Each can have 14 electrons are there, which is given by this 4L plus 2. So L equal to 0, when I substitute L equal to 0, 4 into 0 plus 2, 2. As we had seen this before. L equal to 1, 4 into 1 plus 2, 6. L equal to 2, 4 into 2, 8, 8 plus 2, 10. And F orbital, F subshell I have not drawn. So L equal to 3 refers to F subshell. And how many orbitals are going to be there, guys? 7 are going to be there. The magnetic quantum number will be -3, -2, -1, 0, 1, 2, 3. 2 electrons in each orbital. So totally we are going to have 14 electrons in case of F subshell. So that's given by this number 4L plus 2. 6 electrons in P subshell, 10 electrons in d sub shell, 14 electrons in f sub shell. Is this clear, guys?
So
Yes.
Yes, sir.
Okay. Magnetic quantum number we had seen already. So for a given value of L, there are 2L plus 1 magnetic quantum number values, right? So when L is equal to 0, your M is only 0, so there is only one value. When L equal to 1, M can be minus 1, 0, 1, so 3 values. When L equal to 2, M value can be minus 2, minus 1, 0, 1, 2, so 5 values. When L equal to 3, M can be 7 values, which is minus 3, minus 2, minus 1, 0, 1, 2, 3. All right, guys. That's it. And so on. So basically, 2L plus 1 values are going to be there for M. That's all. Minus L to L. Clear? So this refers to S sub shell, P sub shell, D sub shell, F sub shell. S, M equal to 0 is the only value. When L equal to 1, it is P sub shell. M is equal to minus 1, 0, 1, 3 values. L equal to 2 refers to D sub shell. M will take from minus 2 to 2, 5. L equal to 3, minus 3 to 3 will be M values, 7 values. Okay, that's fine. So this we had seen. So basically magnetic quantum number talks about orientation. So M equal to 0 usually indicates along the orientation along Z axis as a reference. So as you can see, this we had already discussed, guys. So the various orbitals in D is dxy, dyz, dzx, zxz, x square minus y square, z square. Usually z square is given the M value 0. Okay. This is illustrated in this clearly, guys. So you can also understand the shape of these orbitals. Spherical, which means, the probability of finding an electron is going to be in this region. So when it is dumbbell shaped, we can find the electron either in this, either in the slope or in the slope, nowhere else. So in this region, I can find the electron. All right, guys. So this plane will be a nodal plane. We'll be talking about that. What do you mean by nodal plane? There will be no electron in that region. Okay. And the values of M, L, all these you can look at now. Is there anything that you want me to explain more in this slide, guys?
No, sir.
Okay, great. Okay, we give these names as degenerate orbitals, referring to orbitals having same energy. So we say P subshell has 3 degenerate orbitals, D subshell has 5, F subshell has 7, all these. Right? Threefold degenerate or tri-degenerate. D orbitals are penta-degenerate. F orbitals are going to be hepta-degenerate, and so on. So total number of orbitals in a given energy level is given by n square. Very simple to understand this. Each orbital can accommodate how many electrons, students? Each orbital, whatever it be, px, py, pz, dz, dxy, dz square, whatever it is. Yes. Any orbital can only accommodate what? 2 electrons. All right. We already know that any energy level can contain a maximum of 2n square electrons. Therefore, the number of orbitals must be how many? n square, correct? Let's understand this by taking a couple of examples. So first orbit, if you take, right, n equal to 1, there is only one subshell S, 2 electrons. So anyways, number of electrons is not important, number of orbitals is important. Okay, now let's talk about n equal to 2. Now it has 2s and 2p. So one orbital here, 2p, 3 orbitals are there. So 4 orbitals are there in n equal to 2. When I say n equal to 3, we have 3s orbital, 3p orbitals and 3d orbitals, isn't it? 3d, 5 orbitals are there. 3p, 3 orbitals are there. 3s, 1 orbital, right? So totally how many orbitals? 1 plus 3, 4. 4 plus 5, 9. Correct. Now when n is equal to 4, guys, we have one 4s subshell, 4p subshell, 4d subshell, 4f subshell. You know that 4f has 7 orbitals. 1, 2, 3, 4. Correct? Right. 4d has 5 orbitals. 4p has 3. Right? And 4s 1 orbital. So can you calculate and tell me how many orbitals are there totally in 4th orbit? 1 plus 3, 4 plus 5, 9, 9 plus 7, 16. So 16 orbitals are here. Here we have 9 orbitals. Here we have 4 orbitals. Here we have 1 orbital. So basically, if I know the principal quantum number, it is enough. So number of orbitals will be just n square, guys. 1 square, 2 square, 4, 3 square, 9, 4 square, 16, and so on. And the number of electrons that can be accommodated is 2n square. Why is it 2n square? Because every orbital can accommodate a maximum of 2 electrons. That's all. Clear, guys? So is it clear, guys, to everyone?
Yes, sir.
Excellent. Okay. So we have already seen that, Schrödinger's wave equation will give us some results. So it will basically give us, this is the way we will present the solution, okay? The Schrödinger's wave equation. So the first number indicates principal quantum number, second one indicates azimuthal quantum number, and the third one indicates magnetic quantum number. Come on, tell me, guys, now. 4 refers to 4th orbit. L equal to 2 refers to which subshell, guys? What is it? L equal to 0 is S. L equal to 1 is P. L equal to 2 refers to?
D subshell.
Exactly. And M equal to 0, I told you, refers to Z orientation. So the name of that subshell is Z square. So this refers to 4D Z square orbital. More accurately, we can write as 4D Z square. Clear, guys?
Yes, sir.
Yes, ma'am. So let me give you some work now. Suppose, let's say I'm giving you wave function 3, 2, 1. Let me know what is the subshell I'm talking about. What is the... Or if you want it simple, I'll make it 0. Come on, tell me, students, which orbital am I talking about? Quick.
3D Z square.
That's it. Perfect. Third orbit. L equal to 2 refers to, this is M, guys. This is L, guys. This is, sorry, this is M. This is L, this is M. So principal quantum number is 3. So third orbit. L is equal to 2. So D subshell. M equal to 0, I told you that it refers to related to z axis, z square. Okay. One more.
3s z square, sir.
Guys, see here. This is m, this is n, this is l, this is m. L equal to 1, what is it, guys? Is it yes?
It's P, sir.
Very good. So how do I write it? 3
P.
P. I told you m equal to 0 refers to z. That's all. 3p is z. Are you clear?
Yes, sir.
Suppose if I write instead of 0, if I write minus 1, then you can say 3p x or y, doesn't matter. Or if I give plus 1, again it could be 3p x or 3p y. Clear, guys? Come on, tell me. What is this? Quick.
Forest.
Forest.
That's all. This is principal quantum number n, this is L, this is M. 4, then L equal to 0 is S, that's it. And M equal to 0, only one orbital. So there's nothing else to mention. 4s orbital, that's it. That's all, guys. Isn't it simple? Clear?
Yes, sir.
Awesome. Okay, guys. So whenever it is S, right, magnetic quantum number will be 0. L will also be 0. Spin quantum number, nothing to worry. So inside an orbital, the moment I get into an orbital, one electron, if it's spinning in anti-clockwise direction, another electron will be in clockwise, right? So whenever an electron is spinning in clockwise direction, we assign a number m to be equal to plus half, and when it is anti-clockwise, we assign a number m is equal to minus half. So inside an orbital, an electron can have a m is equal to plus half or minus half. So that is why we have Pauli's exclusion principle. What does it say? Come on, everybody. Anybody?
No two electrons can have the same set of 4 quantum numbers.
Yeah, sorry guys, I'll put S. Spin quantum number is S. Okay, correct. So even if I say, let's say n is equal to 3, this is let's say 2, this is 0. Which orbital are we talking about? Quick.
The third orbital.
Third orbit, third orbit.
Yeah. Third orbit.
Which orbit? Which subshell?
D subshell.
Good ma, D subshell. And m equal to 0 z square. Okay ma?
Yes, sir.
So we reached till that point. But one electron will have spin quantum number as plus half. Another electron will have what? Minus half, isn't it? Correct or not? The one which is spinning in the clockwise direction will have same NLM values, but S value alone will change, correct or not? For the clockwise spinning electron inside the 3D Z square orbital, correct?
Sir, I didn't get that.
No, it's very simple. See here, okay, I'll give a different number now, NLM, S. These are the 4 quantum numbers, correct?
Yes, sir.
Okay, N is let's say 4, L is let's say 1, M is let's say 1, okay? Now if I give you NLM value, where will you be boiling down to? What will you know? You will know which orbital I am talking about, correct or not?
Yes, sir.
N equal to 4 refers to 4th shell.
Yeah, sir.
L equal to 1 refers to p subshell.
Yeah.
So with these two pieces of information, I am able to come to 4p, correct or not?
Yes, sir.
4p, I am having 3 subshells, correct?
Yeah, sir.
And m value will be -1 or 0 or 1. When m is 0, it refers to 4p set, all right?
Yeah, sir.
When m is -1, it may be 4px. When m is +1, it may be 4py. Are you getting it, guys?
Yes, sir.
So, with this information, I have got till this point where I have come to the particular subshell. Is this clear?
Yes, sir.
So, I have boiled down to that subshell. Now, this fellow will be the fellow who will be rotating in which direction? Clockwise direction, correct or not?
Yes, sir.
There will be another fellow who will be there, who will be moving in. One will be spinning in clockwise direction, another will be spinning in anti-clockwise direction. See that orbital, how many electrons can it accommodate? Any orbital, how many electrons can it accommodate?
2.
2. So, this will be 1 electron. The minus half will be another electron. 4, 1, 1. 4, 1, 1 plus half will be representing 1 electron which is staying in the 4py shell, subshell or orbital. And 4, 1, 1 refers, minus half refers to another electron which is going to be there in the same orbital but with anti-clockwise spin. Is it now clear?
Yes, sir.
Yeah. So that's why Pauli's exclusion principle says at least even though they occupy the same orbital, their n value will be same, L value will be same, M value will be same. At least they will differ by S value. Clear? Just like no two students can have the same roll number, no two electrons are going to have same value for all the 4 quantum numbers, correct? 3 values, 3 quantum numbers may be same, but the 4th one will definitely be different, right? Is it clear?
Yes, sir.
Okay, students. So that's fantastic.